Today we're going to talk about chapters 7 and 9. So this is the lecture for today and tomorrow. On Thursday, there will be a short lecture on APA style. That's all, a video there. And then Friday, no lecture. Spend that whole time working on putting together your proposal. So essentially today we're going to talk about statistics. And it's not going to be very in-depth. It really will be about how to choose the statistics that you're going to use for your proposal. And so it's more about an understanding, like the theory behind this statistic, what it is, instead of how to do it. So there's two basic groups of statistics. There's descriptive statistics and there are inferential statistics. So descriptive statistics are the statistics that tell you about the sample. So these are statistics are like ways of making a statement about a group of people. You could think of it that way. And so a descriptive statement tells you about the sample, describes the sample. So for example, what is the average age in this sample? An inferential statistic, or as a group, inferential statistics infer like a truth from the sample. And so you could say, well, we know that in this group, the average age was 17. That's a descriptive statistic. An inferential statistic will say how the group compares to something else. And so it helps you infer some truths about that sample. So you might say, well, we know the average age of people that are at Southern Virginia University is, I don't know what it is, but let's make it up. Let's say the average age is 21.3. And this sample, the group, their average age was 17. And so you could say this average age of the group versus all of the students at SVU, two different numbers. They are statistically different. And so that's an inferential statistic. It tells you something, that your sample has an age that it is significantly lower than the average age at SVU. So let me just be clear about the word significant here. Significant doesn't mean big. I know in the regular word means significant. It means kind of like a big difference. But a significant difference only means that it's at a level where the statistic says this is not likely to be by chance alone. It's more likely that this is a real difference, not just a chance difference. And so in order for it to be a real difference, it has to happen less than 5% of the time. That's what the idea is. We calculated the probability of this happening any less than 5% of the time. That's what the statistic is doing. And so the P level is set at 0.05. That's 5%. That means if this happens any more than 5% of the time, then we're going to say maybe there's not a real difference. But if it happens any less, equal or less than 5% of the time, then we're going to say, okay, this wasn't by chance. It's really unlikely that you would get this just by a random chance. It's more probable that there's a real difference because you would only get this result 5% of the time if you were looking at it by chance. And so we say, therefore, that result is significant. It doesn't mean that result is therefore big. So in statistics, you can't say it was really significant or very significant. It's just either significant or not. And so you have to kind of let go of the idea of significant and just figure that this is the only thing it means is that it's less than or equal to a 5% chance that you got this result by chance. And so when you describe, what you're saying is, here is like the descriptive statistics, you're describing like the average. What's the average? How much variability is there? The inferential statistic will say, okay, I'm seeing these two average. One is 16, one is 22. Sample mean A, 16, sample mean B, 22. That's what I know about them. I'm describing them. But if I want to know if these two means are different, is 16 different than 22 given the sample? Then I have to do an inferential statistic to see if these two means are any different. And so that's where the rest of the story matters. So if you say, well, here's two means, 16 and 22, you might say, well, of course those are different. But what if the variability is huge in these two samples? Let's say the range goes from -75 to positive 10,000. And so you have a score of 16, and then you have a score of 22, and the range is huge. And then there's a ton of variability. And so then getting a score of 16 and a score of 22, not really different. And so we would say that different is not significant. However, if the range is much smaller, the variability is much smaller, then it might be a statistically significant difference. So that's why you have to have all this information in order to infer whether or not those two means are actually different. When you do descriptive statistics, you're looking at two things. You're looking at central tendency, which is the first thing. What is about the middle of the group? And so the middle of the group could be easily described as the mean or the average. That works when things are pretty evenly distributed. Or the middle of the group might be better described as the median. So the median is the middle of the group with half of the scores above and half of the scores below. So if you have a ton of scores that are on the low end, and then about 4 scores that are on the high end, then the average might not be a very good way to demonstrate what the average person looks like. The mean might not work because it might be skewed by extreme values, etc. So you might use the median. A lot of times we use the median to describe home values. And that way homes that are really, really expensive don't end up making the average higher than it really should be. If you have a bunch of homes and they're all valued around $100,000, and then you've got 3 homes that are $1 million, then what's going to happen is when you calculate the average home value, they will be higher than 100,000 because you've got those 3 homes that are $1 million. And so that will make the average look higher than is really representative of your sample. And so you would use the median in that case because there is skew. And so that distribution is skewed toward values of 100,000, and then the values of 1 million it's kind of lopsided. So you would want to use the median. Mode is when you're picking the most frequent number as your best example of what the central tendency of that distribution is. Mode is not used very much. Variability is the other measure you want to know about. So you want to know about central tendency, but you also want to know about variability. In other words, what do all the rest of the scores look like? Are they all kind of around 16 to 20? Or are they between -75 and 300? It's going to make a difference in understanding your population when you look at variability. And so some of the things that are involved in variability are range, which is the lowest number and the highest number, or the standard deviation. And this gives you a sense of about how much space is between all of the numbers, which is kind of a weird way of saying it's the average difference between the scores and the mean of the distribution. So you take the average number in the distribution, and what's the average difference between all the scores and that average? And then you get a sense of the standard deviation. I have included a video that goes a little more in depth into this for you to watch to get maybe a more clear idea. I think it's useful to have different people explain it. Variability is kind of an interesting concept, and it just might take you a second to get your head wrapped around it. It's not the same thing as mean, median, mode. Variability really captures how much difference there is in this group. Are they all kind of the same, or is there a lot of differences? Is the range huge and there's a lot of scores scattered throughout? Is the range small and most of the scores are just a few points away from each other? That gives you a sense of the variability. So for example, if you're wanting to describe your sample, and you're going to do this for your research proposal, you won't actually describe the sample because of course you didn't collect the sample, but you're going to discuss your plan for describing the sample. And so you're going to want to discuss your plan for descriptive statistics. And so instead of saying we had a bunch of people involved in this study, which gives you really no information, or even we had a bunch of people, 75% of them were female. Okay, well, that's nice, but you still want more information. And so if you go to the 75% were female, mean age was 40, the standard deviation was 5, then you really have a sense of the group of people you're looking at. And you could say, okay, if the mean age is 40 and the standard deviation is 5, and I have a 21-year-old, they're pretty unusual in this group, especially if it's a 21-year-old male. Pretty unusual, maybe not even part of this group. And so those descriptive statistics will include measures of central tendency and variability. Inferential statistics then apply what we found from the sample to the population. Sometimes you get a sense of how likely it is that your findings are really just unique to your sample, or if they are connected to or on target for the basic population. And so what you're trying to do here is you're trying to prove the null hypothesis. You want to prove that to be false. And so here, actually, let me just fix this idea, because I'm seeing where this might be confusing, the idea before, on target for the overall population, p-value. Okay, that makes it look like population is p-value. That is not what p-value means. I'm seeing this now on my slide, so I don't want you to be confused. P-value does not mean population. The p-value is the likeliness that your findings are either by chance or more realistically applied to being true. So that's what the p-value is. It's the likelihood that the likelihood of this occurring by chance. So we'll do a couple examples where you'll get a better sense of that. And so overall, what you're trying to do is prove that your null hypothesis is false. So the null hypothesis is the hypothesis of no effect. And in the scientific method, what we do is, instead of trying to prove the alternative or the scientific hypothesis is true, we don't try to prove that that hypothesis is true. We try to prove that the null hypothesis is false. So this may seem like a little bit of just like a weird logic problem or a philosophical thing, and yes, it is a philosophical thing. And this is how science is set up. Science is set up in order to prove the null false. So the null hypothesis is the hypothesis that there's no difference between the groups. And so let's say I've got that group that we talked about, a group of people at SVU whose average age is 17, and a people at SVU whose average age is 20.3. And so the null hypothesis would say there's no difference between those two groups. Or let's say I have a group that has a score on the love of chocolate ice cream test, and their score is 77 out of 100. And then I've got another group on the love of chocolate ice cream test, and their score is 98 out of 100. So the null hypothesis would say there's no difference between those two scores. A 77 and a 98, they're just about the same score. And so what we try to do with our statistics is prove through statistics that the null hypothesis is false. Okay, so the null, there's no effect. Think null, dull. There's no effect. Null, nothing, nada, dull. There's no effect. So in any hypothesis, the null hypothesis would be, it's not the opposite, but it's that there's no effect. And so if the hypothesis is girls who ride orange bikes go faster than girls who ride green bikes, then the null hypothesis won't be girls who ride green bikes go faster than girls who ride orange bikes. No, the null hypothesis is there's no difference. Nothing. It's boring. You know, so the flipped hypothesis would be more interesting than, well, there's no difference. It's just nothing boring. So the null hypothesis is there's no effect. So when you're looking at the null hypothesis, there's two ways you can be wrong. Either you're right, there's no effect there, but your study said there was an effect. And so the truth is that there isn't effect, but your study said there was. So then you're wrong in a type 1 error. So your study finds a difference that isn't real. And so basically it's like saying, well, your study found these numbers by total random chance. And so if you did another study, it wouldn't come up with those numbers because your numbers were weird. You got those by chance, something weird happened, and you just randomly by chance got those numbers. And so your numbers are wrong. Your study gave you the wrong conclusion, and the truth is that there is no effect. Orange bikes, green bikes don't make a difference. And the fact that your study found that it did was just an anomaly. Okay, that's a type 1 error. A type 2 error would say the truth is that, yeah, there is a difference. Orange bikes are always faster than green bikes, always. There's a difference. However, your study didn't find that difference. So either your study wasn't good enough, you didn't do it well enough, you didn't get enough people, or you got your numbers kind of by chance. So type 2 says the truth is that there is an effect. However, your study didn't find it. And so if you do a type 2 error, what you're saying is you didn't find an effect that is really there. If you do a type 1 error, what you're saying is your study found that there's an effect, but the truth is that there isn't an effect. So that's type 1 and type 2 error and the null hypothesis. You'll get a chance to play with that in lab 32. Here are some examples. I just like to pull these from my current Reddit subreddit feed on science. And so it just gives us some great little studies that we can look at. So here's one study that says smell may shape how brains process memories. And so if that's a hypothesis, smell shapes how your brain processes memories, then the null hypothesis is, remember, that hypothesis of no effect. And so smell doesn't have any effect on memory processing. So the scientific hypothesis is also called the alternative hypothesis. Either one, same idea. Smell does affect memory processing. Null hypothesis, there's no effect. If there's a type 1 error, what would happen is the truth is smell has no effect, but we found that it does have an effect. And a type 2 error would be if the truth is that smell does have an effect, but we find that it doesn't have an effect, that's a type 2 error, that you just couldn't find what was real. Okay, next example. People with behavioral addictions have losses in gray matter, your brain gray matter volume, comparable to people with substance abuse. And so if you have a behavioral addiction, your brain's gray matter volume loses comparable to people with a substance abuse addiction, right? So the gray matter loss may not just be about the substance abuse, it might just be about the addiction piece in your brain, right? So the null hypothesis, right? So obviously the alternative or the scientific hypothesis is just what it says. Behavioral addiction has loss in gray matter just like people with substance abuse. That's the alternative or the scientific hypothesis, the alternative to the null. The null hypothesis is that gray matter volume is not comparable between people with behavioral addictions and substance abuse, okay? It's not comparable. So a type 1 error would be what you find is that there is an effect, right? But the truth is that there isn't. And so in a type 1 error, what you would find is behavioral addictions look the same as substance abuse, when the truth is that they don't. Okay, so the type 1 error, it's sort of a theoretical idea. You have to know what the truth is. We may not know what the truth is, but here we're saying, for the sake of theory, we're saying that let's say the truth is is that it actually isn't, it isn't comparable. And your study showed that it was, so that's a type 1 error. Or let's say the truth is that it is actually comparable, like the alternative hypothesis here. Let's say that we know that's what the truth is, but your study didn't find that. And so your study missed. And so here you can see it's like having either a false positive or a false negative. So a type 1 error is kind of like a false positive. It's actually not true, but you found that it was true, so it's a false positive. Or type 2 error would be like a false negative. You're showing that it wasn't there, but it actually is there, so you just missed it. So I think sometimes if you think of type 2 as a miss, like I looked for it and I missed it, I missed the reality, then that might help. Okay, next example. Insufficient sleep in childhood can increase your risk of mental health issues. So the null hypothesis would be sleep is not related to your risk of mental health issues. A type 1, right, the false positive, we would say, oh, we found that insufficient sleep increases your risk of mental health issues, when the truth is that it doesn't. So again, we have to imagine, if you're going to play this game, you're going to have to imagine what the truth is. Sometimes we know the truth, sometimes we don't know the truth. So type 1 and type 2 errors are theoretical. They're theoretical errors. And so here are some other examples. I'll do 1 or 2 more for you. Skipping breakfast is linked to a greater risk of a depression. The null hypothesis would be, think about it, there's no effect of skipping breakfast. Skipping breakfast has no effect on your risk of depression. Whether or not you skip breakfast doesn't make a difference. That's the null hypothesis. Okay, type 1 error would be that you found that skipping breakfast really is linked to a greater risk of depression, when the truth is that it's not. So you have a false positive. And so if your study finds that, if your hypothesis is skipping breakfast, greater risk of depression, and you find that that's what your data show, you don't know necessarily that that is a type 1 error. As far as you know, you got the right result. And so what happens is you publish your results and you say that, okay, this is what I found. Skipping breakfast really makes a difference in terms of your risk of getting a mental health disorder. And so you're going to assume that that's the truth, because you don't know what the larger truth is. And you won't know unless you go back and you replicate your study. And so let's say you replicate your study and you do it 4 more times, and all 4 of those times show that skipping breakfast has no relationship to risk of mental health disorders. Then you would say, okay, so that first study, I can't replicate it. So there's something weird about that study. It must have been a type 1 error. Hopefully that makes sense. That's why replication is really useful. The other thing that we do to lower our probability of getting a type 1 error is we make sure that our statistics are set at that p = 0.05 level. In other words, if we say the only way you could get these results and have them be significant is if there is only a 5% chance that you got these results by accident. You know, it's like 95% chance that these results really are accurate, or that these results really are showing a significant difference. And so we set that p level at 0.05 in order to protect against type 1 error. So let me say that again, because this is important to realize. We're setting our p-value at 0.05 so that we lower the probability of having a type 1 error. So it's less likely. And so we're saying, in order to say this is statistically significant, we have to get these results by chance less than 5% of the time. That makes it unlikely that this result is by chance. That's lowering the probability of our type 1 error by keeping the p-value at 0.05 or less, okay? So a type 2 error would be that false negative. You find that there's no difference, but the truth is that there really is. And so let's say your study said, well, I think skipping breakfast is linking to a greater risk of depression, and then you do the study and you don't find that your hypothesis is supported. Your study shows that there's no difference, that skipping breakfast doesn't seem to link to a bigger risk of depression. Then if the truth is that it does, then what happens is you have a type 2 error. There is an actual difference there, but somehow your study didn't find it. You missed. It's a miss. Okay, so that's the type 2 error. Next example, daily supplementation of vitamin D is superior to less frequent. So let me just tell you one thing about this. In terms of immunity, daily supplementation is superior to less than every day. That helps with your immune system. There are other benefits of vitamin D that you can still get when you don't do it every day. But if you want those immune benefits, then every day is definitely superior to less frequently than every day, just FYI. And so let's say your study examines daily supplementation and immunity, and it finds it makes no difference. Okay, so that would be a type 1 error or a type 2 error. Let's say, so if the truth is that daily supplementation helps immunity, but your study finds that it doesn't, then you've got a miss. So that would be a type 2 error. If your study finds that it doesn't and the truth is that it does, you have a miss. The null hypothesis would be that there's no difference, right? Okay. We never actually accept, this is like an English thing, a word choice. We never accept the null hypothesis. And so I know it might feel a little like this is just semantics, but just work with me here. We just never accept the null hypothesis. What happens is, since you don't know what the truth of the universe is, we can only collect evidence that points to what might be the truth. And so when we talk about the weight of the evidence or the bulk of the evidence, that's really the kind of thing we're talking about. What we're saying is we don't know the truth. We're just collecting a lot of data. And so then the data we're putting on this, like the scales of justice, and you have in favor, not in favor, and the bulk of the evidence is in favor. And so we think that's probably the truth, but we never ever really know the truth. We might end up having 1,000 studies that point to the same thing. And then you can say, well, I'm pretty sure this is the truth. But strictly speaking, in the scientific method, we don't know anything. We just have the bulk of the evidence. So we make the assumption that we don't know the evidence, or we don't know the truth, sorry. So therefore, you don't have the evidence to reject the null hypothesis. If you don't have that evidence, you can't just accept it. You can't say, well, I accept that that's true. Instead, your job is to just keep getting more evidence and adding to the bulk of the evidence. And so you either reject or retain the null hypothesis. You don't accept it. So you never accept the null because you might have a type 2 error instead. The null may be likely, but it's never accepted. You never really know it's true. Okay, if this is difficult, reread the text, look at page 166. All right, so now, so the descriptive statistics, null hypothesis, type 1 error, type 2 error. I'm hoping that that's pretty clear for you. Next, we're going to talk about inferential statistics. So if you want to understand the frequency, how much something happens, then you're going to use descriptive statistics. So for example, how many SVU 18-year-olds went on a date last month, the number of 18-year-olds, the number of men or women, the number of majors, all of these are descriptives. If you want to understand if there's any sort of relationship between two variables, so instead of just reporting straight up frequency, if you want to say, well, is there a relationship between different majors? Maybe more 18-year-olds who are majoring in music went on dates as compared to 18-year-olds who are majoring in, I don't know, botany. So that requires inferential statistics. You're comparing two groups, and so you need inferential statistics in order to compare groups, in order to do anything association or causal. And so if one of your continuous variables seems to be associated with another, that's an inferential statistic for an association study, and we use correlation. And so if you're doing an association study and you're trying to compare one thing to another, I'm trying to look for an example here. Okay, I found my my sheet of examples that I can use. All right, so let's say you are looking at the association between extroversion of a person and what kind of dog they have, or their aggression of their dog. So you want to link, does a person who's extroverted tend to have a dog who is less aggressive or more aggressive? You want to know what is the relationship between those two. And so you're going to look at a correlation. What's the correlation between your dog aggressiveness and your personality extroversion? Okay, so those are going to be two continuous variables. You could do it when you have a dog that's either yes or no in aggressive and a person that's either yes or no with extroversion. You could do two categorical values and still do essentially a correlation, except the statistic you use is not a Pearson-R correlation, it's a chi-square. It's still a measure of correlation. A correlation with continuous variables is always better because it's more powerful. You need more people to do a chi-square to see an effect that is there. You need more people. So if one goes up and the other goes up, let's say the person's extroversion goes up and the dog's aggressiveness goes up, then you would have a positive correlation. If one goes down, if the lower your extroversion is, the lower your dog's aggressiveness is, you still have a positive correlation because they're both going in the same direction, okay? One goes up and the other goes down, then you have a negative correlation or an inverse correlation. And so it goes between 1.0 and negative 1.0. So if it's 1.0, you have a perfect positive correlation. If it's negative 1.0, you have a perfect negative or inverse correlation. If it's like close to zero, let's say it's 0.07 or 0.09 or something like that, or negative 0.09, then you have no correlation. There's no relationship between those variables. And so that inferential statistic correlation is probably what you're going to use in any sort of association study. So let's say you have students who are members of certain groups, and you want to understand, does group membership make a difference in terms of whether or not they drink more or less? That could be an association study. It couldn't really be a causal study because I think you can't assign people to groups and drinking. Because what you're looking at is something in those people that make them choose those groups and choose their drinking. And so you're really looking at an association observational study, not a study where you're trying to manipulate that variable. And so you could look at the correlation between particular clubs and drinking. You could also look at it in another way, which we'll bring up when we look at t-tests. But here you're looking at club membership as one variable, which would be then categorical, right? And then amount of drinking as another variable, which would be continuous. You can still do a correlation that way. So the type of correlation statistic depends on whether your data are continuous or categorical. If you want to look at group differences, and so let's say you've got a group that is in the marching band and a group that is in the chess club. Is there a difference between those two groups in terms of how much they drink? Then you're going to look at a t-test. So you have two different groups and one measure. Is there a difference between those two groups in drinking? What you do is you use a t-test. The t-test basically looks at the average or the mean of one group versus the mean of the other group and looks at the variability in each group. So that are these two means really different or are they same? can you say they're not different? So if they're actually different, then you have a resulting t-value, and that t-value gets compared to a chart, and then you get a p-value. The p-value will tell you, is it, what are the chances of getting this by random chance? And if it's less than 0.05, then that t-value is statistically significant. And so choosing the right statistical test for your research design, here's how to keep this simple. Look on page 214. There is a figure there, figure 9.2 on page 214. This is the primary thing we're going to look at in chapter 9. And this chart will help you figure out what you're going to do in your study. And so everyone's going to do descriptive statistics. And so think about the numbers you're going to get and how you want to describe them, so we know basically a picture of what you have. And so of course you're going to want to describe your people. You know, what's the average age, what's their average maybe education or their gender, or whatever the relevant variables are for you. Maybe if you're doing that dog study, it might be how many people live in the city, how many people live in the country, etc. Excuse me. Or if we're looking at temperature and memory, what are people's average memory scores before the temperature changed in their study environment? We want to know that. And so you're going to have those descriptive statistics. Then you're going to test your relationships. So after you do the descriptive statistics, then you do the inferential statistics, where you're not just describing your sample. What you're doing is you're looking at, did your independent variable make a difference? Or is your association what you would call statistically significant? So you have 3 different ways of basically comparing scores, comparing means. Let's say you have 2 groups and you want to compare those groups on one variable. That's one way. Or you maybe have 1 group and you want to see how they compare to the average score. And so let's say you're looking at a group of SVU students and you want to see how do they compare to the national average of college students. That's another way of comparing a mean. Or you have more than 2 groups and you want to look at their average scores compared to each other. That's another way of looking at means. So for example, let's say you have 2 groups and you have the study eating vegetables or fruits versus cereal for breakfast. And you want to look at the impact of that on anxiety. So 2 groups. 1 group has vegetables and fruits for breakfast. 1 group has Fruit Loops. You got to think about, when you do your study design, how long are they going to eat like this? I would suggest more than 1 day, maybe 2 weeks. I don't know. But you have to look up previous research and see what makes sense when you design your study. So if another study found that people who change breakfasts, it takes an average of 6 weeks for that breakfast to have any impact, then in your study, you want to reference that old study and say, hey, Brown and Brown, 1997, found that it takes 6 weeks for breakfast to really make a difference. And so in my groups, then we're going to eat this way for 6 weeks. And then after 6 weeks, then we're going to take our anxiety measure. Okay, so you have 2 groups, veggie fruit breakfast versus Fruit Loops breakfast. Then you ask both of them to take a test that measures the anxiety. And so you probably want to do it pre and post. So they take the test before the study starts at the beginning of the 6 weeks. Then they eat like this for breakfast for 6 weeks. And then they take that test again. Okay, so they've taken the STAI twice. And then what you want to do is compare their scores on that test. And so at the beginning, were the groups equal? Did everybody have about the same STAI score? Because you want equal groups. Of course, if one group already has lower STAI scores, then that's going to affect your outcomes. And so equal groups you get by random assignment. So you want to make sure that your random assignment worked. It almost always does if you have enough people on the study. And then you compare their scores at the end of those 6 weeks on that anxiety test. So at the beginning, they were the same, and then you had 2 groups that ate different breakfasts, and after 6 weeks, you want to look at their anxiety scores again. Are they different? So in order to figure out that comparison, That's an inferential statistic. You're comparing the average mean of one group to the mean of the other group. And so here's what you do. So here's an example. Top one, of course, the kid with the oranges for eyes, veggie fruit breakfast versus Fruit Loops. So you can see as you go through how your study is going to work. You might want to draw out a graph like this. It will help you figuring out what your study looks like. It'll help organize things in your head. You can add it as a figure if you want in your study. That would be awesome, or add it as an appendix. It will definitely help you keep track of what you're doing. So you recruit everybody. This actually, particularly when you write your procedure section, this will be helpful. You recruit people, exclusion, inclusion criteria. They take their baseline STAI, right, for this group of cereal and vegetable fruit eaters for breakfast. So they would do the baseline STAI. You randomize them to the groups. You want to make sure that randomization works because those STAI scores should be comparable in both groups. In other words, the inferential statistic you use, it would be a t-test to look at the difference between group A and group B on that continuous measure of the STAI. You want to make sure that there's no difference. So the result says, no, it says P is not 0.05. P is much higher than 0.05. Both groups are the same. Then you divide them. They're divided into the groups. They eat those breakfasts for 6 weeks. And then you do a follow-up at the end of 6 weeks. Here this says 3 months and 6 months because that was what this study was. But here, let's say yours is at 6 weeks. And the follow-up means that they take the STI again. And then you look at the difference between those two groups. So you had 2 independent samples. They're not the same people, so they're independent. So you took your group and you divided them into 2. You randomized their division. So you've got random assignment to 2 different groups. Because they're different people in those groups, they're independent samples. So that's what you have, 2 independent samples. Everyone takes the test. You have 2 anxiety means, 1 from each group. So are they different? You find out by comparing independent samples t-tests. That's what you use. You're using the independent samples t-test because you have 2 independent samples. So you can see that on that little graph in chapter 9. Little cute fun fact, why is it called a t-test? And you may see in some books, you may see where it's called the student's t-test, or in articles they might say, we used a student's t-test to show this. And I remember when I was in college or in grad school even, nobody explained this to me. They just called it student's t-test. And I was like, well, why is it student's t-test? Does that mean it's like, you know, just for students? Or is it like not very sophisticated? Or what the heck is that about? And so here, I will tell you what that's about. It's called, the test is called a t-value. But the guy who came up with it, his name was William Seeley Gossett. He worked for the Guinness Brewing Company. And he figured this out in about 1908. So the Guinness Brewing Company was very, very interested in making sure all of their product was really high quality. So they loved to run all kinds of statistical tests. Whoops, sorry, let me go back. And so they ran all these tests and they needed to basically manage, like I said, quality of their product. And so this guy was employed by them. And he also agreed that work product belonged to them. And so he couldn't say it was the Gossett test or anything like that because he worked for Guinness. And Guinness wanted his work to be their work because they were paying him to work for him essentially, which is pretty common. And so he couldn't call it the Gossett test because he worked for them. And he didn't really want to, you know, call it the Guinness Brewing Company test either. And so what he did was he published it kind of anonymously, but he called it student's t-test, or people would refer to it as student's t-test because that was his nickname. His nickname was Student. Hey, student, right? And so that's why it's called student's t-test. That was his nickname. And it was used kind of as a term to refer to the t-test, but not in any way meaning what we think of as student. Like if his nickname had been, Daisy, I don't know, coming up with weird things. If his nickname was Daisy, and they would call it Daisy's t-test. So student just happens to mean something else also, but don't be confused. It's just a nickname. It just has as little meaning as Daisy's t-test, student's t-test. So it has nothing to do with being a student. Okay, so taking a look at your study design. Think about your study design. Is your study of association or of causation? There are three things you need in order to establish causation. And even then, we're pretty reluctant to call it cause. And so you have to make sure that your cause happens before your effect. That's called temporal precedence. Your cause has to precede the effect. So in your study, does your cause precede the effect? Then you have to have an association between the two variables. They have to be related in some way. You have to show that they're related. So if I'm saying, well, the cause of me making bread is that there's a thunderstorm the day before, I have to show that there's a relationship. And so I have to, in my data, you have to see that it's not just random chance that I make bread. It has to be related to the thunderstorm in order to show that there might be a causal effect. There has to be an association first, okay? And then you have to control all the other potential alternative explanation. This is the hard part, really hard part. This is all about internal validity, controlling all the other potential alternative explanations. And this is where you want to sit around and think. And so doing homework in this sense is not about jotting down answers. It's about thinking about what else might cause the same effect instead of my independent variable. What else might create that effect? So for example, what if the students who ate Fruit Loops had to compete more aggressively for breakfast than the students who eat vegetables? They had to make sure they got their Fruit Loops, and the people who had vegetables and fruit, well, they didn't have to compete for those. And so what if that competition was the reason they had more anxiety and had nothing to do with the Fruit Loops, right? So that's an alternative explanation instead of just the content of Fruit Loops, sugar, and whatever else is in there. That might be a competitive alternative explanation. And so that would be a threat to internal validity, So you don't come up with that looking it up in a book. You come up with it by sitting around and thinking what else might be going on, or observing, or you run a pilot study, or you interview the people and find these things out. And so it takes some work sometimes to figure out what are the potential threats to internal validity. And so with your studies, you get to just think about what else might make that happen. If I'm going to imagine what are the things might make a difference and that aren't my independent variable that might also affect my dependent variable. Internal validity here is more of an issue when you're looking at a causal study than a study of an association. An association study, you may have a third variable that is the thing that's really creating that association, but there's still some sort of an association happening. And so when you find threats to internal validity, then you don't have enough evidence to say, yeah, this is a causal relationship. You always need more data. And so for the most part, I would say you always need more data to show causality. When we talk about control groups, for example, a controlled study, for example, control in this case simply means we have a comparison group. The comparison group either got nothing or placebo, or they got another treatment. But this is a group where everything else is pretty much the same, except they didn't get the same treatment. And so we control for the other variables. People say it that way. In other words, you have two different groups, two groups that got all the same things except for one difference. And so you're controlling everything else except for that one difference. You're comparing your treatment group to a control group. It's a control group because everything else was controlled except for the one thing that you changed. So, controlled study. There are lots of types of designs. I think we've talked a little bit about this. You could have many types of designs that are causal or associative. Frequency, you pretty much are just doing a descriptive study. You might call it a descriptive cohort study because a cohort is a group of people. And so it just sounds nice. I'm doing a descriptive cohort study, where I'm doing a randomized controlled trial, or non-randomized if it's not randomized, because you can't make people more or less extroverted. You can't change that. And so then you have to say it's quasi-experimental if you can't change that. Or if you're just doing an association, of course, then you're just doing that association. It's not an experiment at all. It's an association study. So here, I think we've discussed some of these, the types of design, just as a little review. Okay, so example number 2. So the first one we did with the fruits and vegetables, we were looking at 2 groups, independent samples, t-tests. 2 different groups. One group ate fruits and veggies, the other group ate Fruit Loops. We looked at their anxiety score at the end of 6 weeks. So let's look now at a 1-group study. So this would be a different kind of study. We're going to use the same example to kind of help you see the difference. So let's look at the effect of eating fruits and vegetables on anxiety. And so you want to compare your group to a known population average. And so we're not running 2 groups. What we're doing is we're running 1 group and then comparing them to the average college anxiety person, or anxiety score. A college person anxiety score. That's what I'm trying to say. Yeah. And so you already know, you look this up. You look up in the manual for the STAI, and you know what the average college student's STAI score is, because it says in the manual, because they've done that research. The STAI is pretty well known. They've done that research. And so you look, here's the average student's STAI score. It's around 37 or 40. So how does this compare to SVU students in general? Or how does this compare to SVU students who eat vegetables and fruits for breakfast? So you only have 1 group. They all take the STAI. You look at pre and post scores, and you compare those scores to average college student scores. So here, this is what this study would look like. You recruit, you enroll. There's no random assignment because you're only looking at 1 group. So you've got the treatment group. They all eat fruits and veggies. They take the STAI and you analyze their scores compared to the average person's, the average college student's score. And so you do this with what's called a 1-sample t-test. It's not independent samples because you don't have 2 samples. They're not independent. You have 1 sample, and the 1-sample t-test looks at your sample compared to a known population mean. That's a 1-sample t-test. How might this compare to your studies? Well, let's see. Let's say you're looking at a study of doing service and well-being. What you want to look at is your group's well-being scores compared to the average college student's well-being scores. What if your group already has higher well-being scores than the average college students? Well, then you can't really say that doing service helps them be higher, because it might be that they're already higher. And so you want to make sure that your students are the same as the average college student. Or you get a whole bunch of average college students and you give them a well-being test and make sure that it is average. So you do a 1-sample t-test to look at that. And then you have them do service and you see if that service made a difference in their well-being scores. And so you're looking at the difference between scores at 0.1 and 0.2, which is not this test, down the line. We'll look at that in a second. Okay, so if you want to compare your sample to a population known mean, then you do that with a 1-sample t-test. So as you're doing this, I just want to give you a little side note that might help you feel like you're doing it right. Because I know there's some anxiety that goes on when you think, am I studying correctly? Am I doing this right? What are the right answers? And so let's look at this just for like a little moment, this idea of deep learning and surface learning. Okay, surface learners want what's the least amount I can do. Okay, just tell me what to fill out. Show me what you want and I'll just plug things in. I just want to reproduce the work, so rote learning, just the basics. I want to know the right answers. Okay, that's surface learning, and it goes away pretty quickly. You don't retain a lot of surface learning, and so you take these classes, and if you only do surface learning, then a year after you took the classes, you're gonna be like, yeah, I have no idea. I don't even know what happened in that class. All I did was, maybe you got an A, but it was very surface learning. Deep learning, on the other hand, means that you are really taking this in. You're really understanding the information. You're sitting with it. And sometimes it takes longer. Sometimes it actually doesn't take longer, but sometimes it does take longer. But this would be where you're trying to figure it out. And so the anxiety that comes from, well, I don't know what the right answer is right away, that's anxiety that came, I think, from high school, where you're kind of used to knowing the right answer instantly and you don't have to work for it. And so that the quality of that learning isn't really good. If you just automatically know the right answer, you didn't have to work for it. You're like, oh yeah, this is what it is. Or, oh, I recognize that right away from my text. Boom, got it. That's still surface learning. It's not part of you. Deep learning is when you take it in and you figure it out. So when I'm asking you to create a research proposal, I'm teaching you all of these parts of research methodology and then asking you to create a proposal. That kind of forces you into some deep learning, where you have to take the principles that you've learned and apply them and put them into this project where you're doing your own thing. And so it's not about looking up the right answer. It's about trying to apply principles you've learned. This is deep learning. And the cool thing about this is that if you have a deep learning style, you end up having lower anxiety than people with a surface learning style. Lower anxiety in your deep learning style. And so if you feel like, oh my gosh, I'm doing it wrong because you're not doing it like you did in high school when you knew all the right answers and you just wrote them down, be grateful you're doing deep learning. You're not doing it wrong. You're doing it right. And just be confident that that deep learning style is really the best bet, and that, hey, less anxiety, that's a good thing, right? So that's your little side note here. Here's another example, 3 different groups. So we did 1 group, we did 2 groups, now we're gonna do 3 groups. If your study has 3 groups, same study, fruits, vegetables, breakfast, etc. 1 group has vegetable fruit breakfast, 1 group has Fruit Loops, and 1 has regular breakfast, what they usually do. And so here you're looking just at 3 groups instead of 2 groups. They all do the same thing. They all take the STA pre, they all take it, they do 6 weeks, then they take the STA post. Then you want to compare the scores of all 3 groups instead of looking at 2 groups, okay? So it's really not a big difference, it's just that you're adding 3 groups instead of 2. So you can't really do an independent samples t-test because that only has 2 groups in it. So here you've got 3, fruits and vegetables, Fruit Loops, and whatever they normally do. And so we're adding that 3rd group. My little sloppy red there is I'm adding a 3rd group. So everything is the same, you're just adding that 3rd group. You have 3 different means, 3 anxiety means. You use an ANOVA, an analysis of variance. ANOVA is an analysis of variance. Sorry, this is a misprint, or a whatever you call it, typing a thing. ANCOVA would be an analysis of covariance, and ANOVA is an analysis of variance. So what you want to know is, how do the groups associate with each other? And so that's the kind of thing that you want to use I'm not going to explain to you how you do it because that's for your statistics class, but in your research proposal, you're going to know, do I have 3 groups? I don't actually think that anyone in this class has 3 groups. I could be wrong, but looking quickly at your projects, I don't think anyone does have 3 groups. But if you did, then you would say, we'll compare means using ANOVA or ANCOVA, depending on it, with its variance or covariance. So here we have 1 group that does both treatments. This is the 4th example. So instead of 1 group that you're just describing, or 1 group where you're comparing their results to a known population, here you have 1 group that has two things happening to it. And so this would be within subjects, if you remember, instead of between subjects. Now you're looking at within subject because you have one group and they have two things that they're doing. They have both treatments. So one group, first they eat breakfast 1 for 6 weeks, then they take the STAI. Then they have breakfast 2 for 6 weeks, then they take the STAI. And you want to see, did their STAI at the end of group 1 or breakfast 1, is it the same as the end of breakfast 2, or is there a difference? So what statistics do you use? You're looking at the same people, 2 different time points. So 2 treatments, but 1 group. You find out by using a paired sample t-test. It's paired because the people in that sample are paired. In other words, one person does breakfast 1, and then that same one person does breakfast 2. And so those 2 people are paired, okay? They're the same people. So you're using a paired sample t-test. So just to review, an independent sample compares the means for 2 groups. A paired sample, not independent, paired sample compares means from the same group at different times. One sample t-test looks at the mean of one group against a known population mean, and ANOVA compares the means of more than 2 groups, 3 or more. Okay, so that's how you compare means. The next thing you want to look at are testing relationships. If you want to pause and take a breather, do some jumping jacks, this might be a good time. And then come back to me, right? So testing relationships. Is there a relationship or not? So you're basically having DTR, mathematically speaking, DTR. It's really easier than an actual DTR. You put the numbers into equation is all you're doing when you're testing that kind of a relationship. So you want to know what kind of relationship is there? Is it a positive relationship? Is it an inverse relationship? Is there a relationship at all? Like I said, easier than your average DTR. So both of your variables are continuous. If that's the case, both of your variables are continuous. Like, for example, does the amount of excitement about research methods that you feel correlate with your grade in the class? Both are continuous variables. And so I could measure the amount of excitement you have for research methods, and then we can look at your grade in the class in terms of numbers from 0 to 600 or something. You use that Pearson R t-test, correlation. And so 2 continuous variables, the Pearson R. If you wanted to predict one from the other, then you wouldn't use a Pearson as much as you might use regression to predict one variable given what you know about the other. And so let's say you're looking at extroversion and aggression in dogs. You might want to predict the dog's aggression looking at the extroversion score of the person. So you might use regression for that. Or you could just straight up use correlation. So you correlate it. Is there a high correlation or a low correlation? It sort of depends on how you want to use the data. Let's say instead of continuous variables, you have categorical variables, like the gender of your classmates versus them, whether or not they do their homework. And so you have a gender as one variable, and so that would be a nominal variable, right? Categorical. The other variable is whether or not they get their homework done. Again, this is a nominal variable. So you use a chi-square. That's what you do. If you have a study where you're using 2 categorical variables and you want to know if they're associated, then what you use is a chi-square test. All right, so that's it for chapters 7 and 9 about statistics. The idea here is you're just figuring out what statistics you will use. Everyone will use descriptive statistics, and tell me what your plan is there. What are the variables that you will describe in your descriptive statistics? And then everybody will figure out what inferential statistic they're using, unless you are only doing a frequency study. So let's say you're only looking at what are the types of narcissism in this population, or what's the amount of narcissism here. You're not comparing it to anything. You're just straight up reporting. In that case, your study is entirely descriptive. There are no inferential statistics involved. It's just an observation study of frequency. nothing else. Okay, but if you have any sort of comparisons or association, I'm looking at, are people associated with the kind of groups they're in and how much drinking they do? Or let's say I'm looking at the type of exercise you do and how much anxiety you have. All of those kinds of things need inferential statistics. And so doing Lab 59 will help you with this because it will just help make things more clear. And so if you look at Lab 59, it will ask you things like, you know, tell me about your study. And then you just write down the answers to those questions. Is your research question about comparing means from different conditions or about testing a relationship? And so you figure out which one it is. And they're basically helping you go through that flowchart that's in the text in chapter 9. And so if you just follow through with the questions, you should be able to tell what statistical test you will use to analyze your data, and then use that test when you write out your statistical plan for your research proposal. So your statistical plan will look like, here are the descriptive statistics I will use, and then here's the inferential statistic or statistics that I will use. We're going to compare these two groups using an independent samples t-test, for example, something like that. If you can't figure this out, please contact me and let me help you. All right, in terms of class stuff, this is the last week of chapter reading in the book. How about that? It just like feels like it's just gone like lightning. So this is the end. At the end of this week, you will be all done with any chapter reading in the book. This week, what you're going to do is put your proposal together. I'm going to give you details in a sec. You'll put your proposal together and turn that in on the weekend. So I will work really, really hard to give you feedback. Next week, all we're going to do is critique articles. And so you'll read articles before class or before the lecture. You read the article, and then I'll help you go through and critique it. And we'll do I'll help you show you how to do it. Then I'll help you, and you learn a little bit more on your own, and then you do it on your own, and I give you feedback, and then you do it on your very own for the final. Okay, so that's all it is for next week. After this week, you're done with the text. Next week, it's just critiquing articles. I'll give you the articles, and the final exam is learning how to do that article critique, or a smackdown is what I call it, based on what you learn. Okay, so that the end is in sight, right? When you do your proposal, when you put your proposal together, I created a rubric for you. It's in the files. I sent it to you in an announcement. It's in a couple of the modules there for you this week, so it should be really hard to not run into it. I don't know how you can manage to not find it or skip it. So look at that and just kind of plug your proposal into that format. I'll get it back to you as soon as I can when you turn it in. I'll give you comments. Use those comments to make changes so that when you turn it in, the final draft, or the final, not draft, the final actual proposal, you're going to turn that in June 26th, the Friday, June 26th, with all the changes made based on my comments. All right, finally, Lab 32, just really quick to make sure that you understand that. Here, we talked earlier today about what is a null hypothesis, what are type 1 and type 2 errors, what does it mean to retain the null? You don't accept the null, remember? And we talked about whether or not you accept or reject the hypothesis based on the p-value. And that p-value is what is the likelihood that you're just getting this by chance or not. So that will help you as you do Lab 32. Lab 32 is a way for you to really demonstrate that you understand this, or see that you need more help, and go back and listen again to the examples, reread that section in the book. So I hope that helps you with Lab 32. So the next and last lecture for this week is just going to be a brief thing on APA style. So watch that video on APA style. That will help you construct your paper, your proposal using APA style. If you feel very, very confident that you know how to do APA style, great. I love it. Have a great week. Looking forward to talking to you next time.